Welcome to the VG Lab podcast, where we discuss engineering concepts and applications found in everyday life. Hello, welcome. My name is Eric Vasquez. I'm an associate professor in the Department of Chemical and Materials Engineering at the University of Dayton. I do this podcast as part of my teaching and research efforts. Today, we will be discussing about amorphous metals, which is an interesting topic. Let me introduce the guest for the podcast, Brady.
Yep. So my name is Brady Kirkpatrick. I'm a fifth-year undergraduate chemical engineering student here at the University of Dayton. And yeah, it's great to be here.
Thanks for being here. Definitely an interesting topic that we will be discussing. So we have discussed many different types of materials in our class, right?
Yeah.
Ranging from materials with crystalline to amorphous properties. Today, we'll discuss a subset of these materials known as amorphous metals and their applications. Can you describe what amorphous metals are so we get a quick introduction?
Yeah. So I think the best way to introduce amorphous metals is to sort of talk about the two broader class of materials that they sort of take a page from. So the first one of those is metals. So I guess I'll start with the basic history. So some of the earliest metals that were used in broad application were copper and tin, and its sort of derivative alloys, notably bronze. And so this was, 1,000 to 3,000 years ago. They were historically used for tools, weapons, vases, and for many other things. But now when we think about metals, we think mostly of materials like aluminum and steel. So, steel is used in a very wide variety of applications depending on the way it's alloyed, from, in construction, from large buildings to rockets. And then there's materials like aluminum, which is used in a lot of consumer products like cans, and it's even starting to be used more and more in the automotive industry. So these metals have a lot of prolific use throughout society, and they are used based on which properties are desired. So the different alloys, depending on the chemistry. So metals are known for having a very rigid crystalline structure, so very ordered. And packing patterns describe how these structures are classed. So a couple of examples of these are hexagonal close-packed structures, body-centered cubic structures, and cubic close-packed structures. So sort of like I was saying before, it's very ordered, but a lot of these crystalline structures are not perfect. So within packing patterns, you have slip planes, dislocations, so sort of areas in the crystalline structure where there may be an atom missing from the structure. And then you have grain boundaries. And each of these characteristics influence macroscale properties that can be tailored to specific needs. And some of these properties are hardness, brittleness, and ductility. So aside from metals, now I'll talk a little bit about amorphous materials. Some examples include rubbers, plastics, gels, and waxes. And these materials were first identified by their structure in the early 1900s by an X-ray scattering technique, and more recently by electron microscopy. But generally, these materials do not follow any rules of crystallinity, so their structures are sort of random. So if you can sort of think of the way plastics work, is they have very long carbon chains, and they're sort of interlinked together, and depending on their structure, it can be like cross-linked and things of that nature. So to sort of put together both some properties from each metals and amorphous materials, you get amorphous metals, which are also known as metallic glass. And they exhibit properties of typical amorphous materials while being fundamentally constructed from alkaline and transition metals that are commonly found in crystalline structures that make up metals. So a few examples of some of these elements are magnesium, zinc, titanium and zirconium.
Very good. So that was a good introduction coming all the way from crystalline materials, right, that has a structure,
Yeah.
to materials that are amorphous in nature, including metals. So what are some of the first metallic glasses and how were they discovered?
Yeah. So the first metallic glass reported in literature was an alloy of gold and silicon. So typically it was known to be a crystalline alloy with a hexagonal close-packed structure. But it exhibits an interesting eutectic, which is a minimum mixture melting point at 20% atomic weight silicon, and the rest being gold. And this happens at about 636 Kelvin or 363 degrees Celsius. So this melting point is much lower than its constituent parts, being at well over 1,000 degrees Celsius for each of them. And it was found that when this structure was very rapidly cooled, it would solidify into very thin objects with random non-ordered structures, which is very unusual for this particular material's behavior. So they had to apply very high cooling rates on the order of 10 to the power of 6 Kelvin per second. So very, very rapid cooling. And then aside from that, the first bulk metallic glass, also known as a BMG, was an alloy of palladium, copper, and silicon. And this was produced with a suction casting method. So suction casting involves an inert chamber with an arc melter. Components are placed into a mold together, melted at very high temperatures, mixed, and then cooled, usually through water cooling through the copper block mold that it's prepared in. And it was discovered that cooling rate, like I was mentioning before, is one of the biggest limiting factors in amorphous glass production. And too low of a cooling rate will result in the structure getting organized instead of cooling into an amorphous type of structure. So some other preliminary amorphous metals used, rare earth and common metals due to their lower critical cooling rates. Some examples of this include lanthanum, aluminum, nickel, and then aluminum and copper. These exhibit much lower critical cooling rates, such as 10 to the power of 3. So when you bring that cooling rate restraint down quite a bit, then it becomes easier to produce some of these metallic glasses.
Yeah, still the order of magnitude in cooling is quite significant, right? 10 to the 3
Yeah.
power to the third kelvins per second. That's quite fast cooling required for this type of amorphous materials.
Yeah, so when you're able to bring it down by 3 orders of magnitude, then it becomes much more feasible from an engineering perspective to make these metals. And so I guess they can sort of be thought of this way: is freezing of a material before it has a chance to organize into a crystalline structure. So if we think of this typically how we think of metals in a crystalline structure, you're sort of freezing the material so quickly that it doesn't have a chance to organize, and can be thought of as like an extreme order of dislocations in the structure, and making it sort of random.
Oh, excellent. So what other factors are considered in the production process, and are there any other production methods involved?
Yeah, so there's a couple other production methods other than suction casting. But as far as the production process, it's usually separated between pre- and post-processing. So you have sort of forming the material itself is the first stage, and then post-processing it into something that can be applied or used in the real world. So for pre-processing production, there's a property known as GFA, or glass forming ability. So there's many factors that influence the glass forming ability, some of which I'll discuss a little bit later, but it can be thought of as the ability to withstand the effects of crystallization, and cooling rate is a part of this. There's also the critical casting diameter size limit, which is related to cooling rate constraints due to thermodynamics of how heat is transferred into solids. So this is a limit on the effective achievable size of a bulk metallic glass. And this is also related to cooling rate as well. As you can imagine, there's conductive cooling that has to occur through the material as it's cooling. And the larger you make the bulk size of the glass, the harder it is to conduct heat away from the center of that bulk structure. So some other factors that influence the GFA are atomic size ratio, liquidus temperature, heat of mixing, and competing crystalline phases. And then, as mentioned before, component selection for the alloy is also a very important factor in mediating the effects and maximizing GFA. So there's many different alloys that exist for metallic glasses, and it's a constantly ongoing research for that. But as far as other production methods are concerned, one of them is high-pressure die casting. So this is where molten metal is dosed into a shot sleeve, where a piston will then inject molten metal, filling and pressurizing the model cavity. And this method is most likely well known for its proliferation in the automotive industry for casting aluminum alloys. I remember reading a few years ago about how Tesla was integrating this and building new manufacturing plants with something called their gigapress that uses high-pressure die casting to cast the frame of their vehicles. So this is a very neat method that's used even for crystalline structure purposes. But there's also low-pressure die casting, and then centrifugal casting. This involves a cylindrical copper block with a mold cut out in the center. The block is rotated by a motor with a transmission for variable rotation speeds. And above the mold is a quartz injection chamber where a high-frequency power supply is able to melt the components in the chamber together through arc melting before injecting into the spinning mold. But so moving on to some post-production, this is mostly concerned with preparing the material for its intended purpose, sort of like I was mentioning before. And there are many methods that are used to do this. So a couple of them are thermoplastic forming, or TPF, cold rolling, joining processes, electrodischarge, and microforming. And so I'll go into detail for a few of these, the first of which being thermoplastic forming. So this is also done through a molding process. It requires the metallic glass to be produced in very thin sheets, and then the sheets are forced into a patterned mold through perforation, and then multiple mold sections are joined together through parallel joining, and then the structure is demolded with joint sites connecting the sections. And some researchers, Liu et al., formed metallic glass in sort of a honeycomb type structure through this method. But one downside to this is that TPF requires very precise molds, which can be sort of difficult to manufacture and easy to damage. Microforming is another post-processing method, and this is done through various methods such as microelectrical discharge and micromachining. Most of these methods are done with a high-power laser. The use of this laser allows for intricate micro-machining capabilities. And an important note for this is that fabrication through these processes can introduce a significant amount of heat. And so you can imagine if you keep this localization of heat on your material while you're trying to form it, it can cause it to achieve its glass transition temperature and sort of melt the material on a localized spot, and then when it recools, it'll form into a crystalline structure, which is sort of different from the rest of the amorphous type structure that the material is trying to achieve. So that's one important note to make about that. One way to bypass this is to pulse the laser. So you allow cooling between pulses, and so it doesn't achieve that glass transition temperature and stray away from the amorphous structure that's desired. So yeah, there are some pretty intricate production and machining processes, and this is all due to the way metallic glasses are formed.
Very good. That was a great introduction to the pre and post processing methods
Yeah.
that are used for this type of materials. So talking about the lasers, that also reminds us of additive manufacturing, which we discussed in our previous podcast. So it's a good connection that we make here, where you said that a pulse laser is required, right?
Yeah.
For the high cooling rates needed.
Right.
Right. So this is interesting. And with regards to the properties, what are some of the characteristic properties of metallic glasses, and how are they different from metals and other amorphous materials?
Yeah. So something interesting that initially got me interested in studying metallic glasses stems from one of their mechanical properties. So specifically, they tend to have low mechanical damping or low dissipation losses. And it was around the time we started discussing amorphous metals in our class is when I came across a YouTube channel by the name Nile Red. And he published a video where he was producing a metallic glass called, and the specific alloy that he was producing is called Vitrolloy 1. And this is also produced using a casting method. And there's various other vitrolloy alloys that essentially either change the ratio of their elemental components or they will change the alloy components altogether. But Vitrolloy 1 specifically is an alloy of zirconium, beryllium, titanium, copper, and nickel. And the goal of what he was trying to achieve was to produce a metallic glass that exhibited this property of low dissipation. So he shows the whole manufacturing process of his casting production, where he has an arc melter that sort of melts all the materials into the mold, and this is all done under an atmosphere of argon, so that there's no oxidation happening during the melting or during the cooling process. And his resulting bulk metallic glass he places on top of I believe it's a stainless steel block, and he drops a ball from height, and it's able to bounce for 40 seconds up to a minute. Whereas if you drop it onto just the stainless steel itself, it would hit a couple times and then just sort of come to rest. So this property of low dissipation, it manifests itself as very minimal kinetic energy losses from contact with the material, and that's just one of the interesting properties that got me interested into looking into these materials in the first place. So, but some other general properties are they typically have pretty high hardness, comparable with many other metal alloys actually, such as hardened stainless steel, which can have upwards of 15 gigapascals of hardness. They also have a very high fracture toughness. They have resistivity that's independent from temperature, which is a very important feature that I'll touch on a little bit in the applications. They have high magnetic permeability. They have high corrosion resistance, and they have no grain structure. So this allows for high precision in castings. And then they have high surface polish. They're not transparent. Sort of a contradiction to the name. I think when most people hear glass, they would think
something transparent.
I'd be able to see through it at least, but no, they're not transparent. Very high surface polish though, so very reflective.
Very reflective.
And then overall they're just generally durable materials. But some of the downsides of metallic glasses are they can be sort of difficult to achieve other material properties if you're optimizing for glass formability, which in most cases you are because of that cooling rate restraint that I was talking about earlier. If you want to maximize for actually being able to form the metallic glass, there can be some drawbacks, such as achieving a desired density for the material. Another downside is they can exhibit low fracture toughness, depending on the alloy. They're not very easily recyclable. They have a pretty slow production rate due to the intricacy of the manufacturing process, and right now they have a generally high cost. So,
Good, good. That example of Bitterloy remind me of another example of liquid metal.
oh yeah,
Yeah, there is a zirconium-based alloy that also has some glass amorphous characteristics.
oh, that's interesting.
Yeah, so definitely when it bounced on stainless steel, right? You said it bounced several times, so it didn't lose energy because of friction, right? That makes them very appealing for coatings, I believe.
Yeah.
Good, good, good. So I can imagine there is a plethora of applications in materials, or how are these properties exploited to be used, and what sort of applications are currently being used this type of materials?
Yeah, so there's a few broad industries, I guess, where metallic glasses are being mostly used right now. The first largest application, I would say, is in the aerospace industry. But applications for metallic glasses are constantly expanding. NASA has done quite a bit of research on metallic glasses for various purposes, but one of which that I'll start with is for protective shielding. So the goal with researching this was to have high hardness and a low density material to be used for shields to protect against space debris collisions with spacecraft. So when I was sort of looking into how they're researching this for application, as we continue to send more rockets up into space for purposes of satellites or for any other purpose, there's a gradually increasing amount of space debris that's sort of orbiting the planet. And so NASA is researching metallic glasses to be used in the shielding so that they can prevent damage to orbiting spacecraft. So one of the tests that they conducted involved a zirconium, titanium, copper, nickel, and beryllium alloy. And then they had to use a second zirconium, titanium, niobium, copper, beryllium alloy. And together they formed a composite from the two, which formed a multi-layered shield that they then tested for various ballistic properties. One of these is that one of the important conclusions from the research that they did on this was that they proved that spalling behavior was observed when impacting the material with debris at velocities as high as 2.8 kilometers per second, and it proved to be an excellent shield. So some other aerospace applications involving the use of metallic glasses are gears. So metallic glasses become more ductile at lower temperatures, which is sort of opposite to the way that typical crystalline metals behave. And so researchers at NASA found that some alloys of metallic glass performed exceedingly well at delivering high torque at temperatures as low as 76 Kelvin. So, one of the specific applications that I guess could be used for this would be with some of the probes or the robots that they're sending to other planets, such as Mars. They require gears in order to be mobile on the planet's surface, and planets such as Mars have pretty low density atmospheres where temperatures can fluctuate very wildly, and if you have temperatures that dip extremely low, the gears can become very brittle and they can crack and shatter, and so this purpose of researching metallic glasses as gears would improve the lifetime or the life cycle of the robot on other planets, and that's what they're being researched for. So But metallic glasses have also seen promising results for solar wind collection, corrosion resistance in aerospace vehicles, and magnetic sensors for detecting magnetic fields in space. But aside from aerospace, there are other industries that metallic glasses are involved in, and I would say probably the second most important industry would be for biomaterials in the biomedical industry. So, in general, metallic glasses show promise as biomaterials through superior properties of strength, wear resistance, fatigue endurance, and corrosion resistance. A metallic glass alloy of magnesium, zinc, and calcium. There has been some research done on this. It may show promise for use as a biodegradable material that shares many characteristics with that of bone, making them useful for uses in screws, pins, or plates to repair fractures. And I think one of the largest reasons for this is because of the inclusion of calcium. It's a very high percentage of that alloy. But magnesium-based metallic glasses also show potential for uses in stents due to higher strength and better corrosion resistance properties. And then aside from sort of the biomedical or biomaterial industry, metallic glasses have shown or are being used in everyday items, such as tennis rackets and golf clubs, due to their low damping, translating to a higher energy transfer to the ball in each of those cases that I just mentioned. And lastly, just some other broad applications that I saw they were being used in are for optical and electrical devices, for use in liquid crystal displays, and for digital data storage. So they have a very broad range of applications, from everyday items to investigating their use in robotics on other planets in the case of NASA. And so yeah, I think there's very broad use in industry.
Very good. Yeah, the applications that you mentioned, right, from tennis rackets to shieldings in aerospace applications, that sounds very interesting. Definitely, there is a lot of room for improvement, right?
Yeah.
With this type of applications, and the magnetic sensors also, I believe, will depend on the type of alloy that you prepare.
Yeah, absolutely.
So the type of alloy is important when we discuss this type of materials. The iron content, I believe, will impart some magnetic properties. We were discussing about some of the magnetic characteristics of these devices as well.
Yeah.
So what does the future looks like? What does the future of amorphous metals look like, in your opinion?
Yeah, so as far as future applications are concerned, it's been shown that they may show promise in the development of fusion energy through the ITER project in France. So there's been some, fusion energy is constantly being researched for and developed in order to hopefully achieve that one day. And as part of the research in fusion energy, metallic glasses are being researched for their resistance to plasma degradation. So, plasma is very heavily involved in the way that fusion energy is being researched right now, and being able to shield against the plasma is a material science problem that they're sort of running into, and so metallic glasses are being researched for that purpose. But as far as continued research goes in other fields, for aerospace applications in particular, seems to be the most promising field from what I've seen from the research that I've done. We've sort of just only scratched the surface here today for what's possible for them. But other desired future developments include discovering new atomic configurations, new forms of alloys. That's probably the largest one, is just, performing research on different alloys and different atomic ratios and things like that. And then the development of a slow solidification process. So if they can get the glass forming ability to not be so heavily reliant on the cooling rates, then they can develop a sort of a slow solidification process, and then further development of formability in general. So I think it's a very exciting future for metallic glasses. It seems like there is a lot more room to grow and a very expansive range. As we were sort of talking about before, is they're used in everyday products such as golf clubs and tennis rackets, all the way up to spacecrafts and robots on other planets. So they've already been shown that they can be applied in a very wide range of applications. It's just a matter of performing the research and the engineering of the metallic glass itself that I think is the limiting factor for their expansion and their use in more broadly.
Very good. Yes, there are definitely a lot of applications that this could go in, right?
Yeah.
I also believe that medicine, energy, clean energy, perhaps can benefit from this type of metals.
Yeah.
Especially due to the corrosion resistance.
Absolutely.
And we can also look at electronics or flexible electronics. I think I was reading about how these materials have also found room in flexible electronics. So they are definitely a material that is of metals, right? Are high conductors, right? So if you can make it flexible, you can produce a lot of different new types of technologies.
Yeah, absolutely.
So let's thank again, Brady, for being here with us today.
Yeah, absolutely. Thank you. It's great to be here. I'm glad I got to be able to discuss this. So
excellent. Thank you.
Yep.